February 12th, 2017, Baz. This is more for you. This is where my mind is going. I'll go ahead and read this out to you and explain a little bit. Formose reactions in stellar metamorphosis. Formose is a portmanteau of formaldehyde and aldose, which is, I believe, a sugar. Abstract. It is hypothesized that the first sugars for prebiotic life are formed during stellar evolution according to the general theory of stellar metamorphosis. They are created by formaldehyde being polymerized by iron-nickel meteors, which serve as catalysts, entering the atmospheres of middle-aged stars such as Jupiter and Saturn. Explanation is provided. Basically, polymerization means you take a molecule, and that very same molecule, you attach another molecule to it, and then another molecule, and then another molecule. So what happens here is the iron enters into the star, the formaldehyde's already present, and it breaks up, and pieces of that iron, the surface of it, allow for or catalyze the reaction. So you'll have a bunch of formaldehyde already in place. The iron will slam into it, and it'll cause those the formaldehyde molecules to combine together. And eventually the molecule gets long enough to where it then reconnects on like a big chain. Think about a chain. It'll bend around, and then boom, you have your sugar. But that's more advanced, from more advanced talk. According to stellar metamorphosis theory, the vast majority of the chemical reactions that occur in the galaxy happen inside of stars as they cool and die, becoming planets, exoplanets. This is in line with the astrochemical principle. One of those reactions is the polymerization of formaldehyde to form simple sugars in the atmospheres of intermediate age stars as iron and nickel react with the atmosphere. The extreme heat of the iron and nickel, the fact that they break up into trillions of smaller bits to vastly increase their surface area for reactions as they smash into the atmosphere, as well as their ease in acting as catalysts to combine a multitude of chemicals together, are all central to the process. In particular, it has been unfortunately accepted in mainstream circles that asteroids can form prebiotic chemicals absent the material and processes required for reactions to take place in outer space, as outlined in stellar metamorphosis. For instance, if an asteroid is mostly iron and nickel, where does the hydrogen come from? The carbon, the oxygen, the formaldehyde? Solar wind impacting the surface of a tiny asteroid would not provide the sheer amounts of organic precursors readily available in the atmospheres of intermediate-age stars. As well, their average velocities as gases would readily exceed the escape velocity of even the largest asteroid, as these are outlined in basic principles of chemical reactions required for prebiotic life to form in the mobility, gravity, container, and volume principles of stellar metamorphosis. We must realize that reactions of an entering asteroid to form prebiotic chemicals take place as the object enters the atmosphere. This means that mainstream claims rely on life being brought here are simply misattributed to the reactions that took place on the asteroid as it enters Earth's atmosphere when it was a lot younger. This hypothesis is as follows. Prebiotic sugars are predicted to form in the atmospheres of intermediate-age stars as iron and nickel asteroids impact them, which act as catalysts on large scales. Given they contain considerable amount of hydrogen, carbon, oxygen, and the chemicals comprising the specific combination of the three, in this case being formaldehyde. That's it. This is due to the Formose reaction, as discovered by the chemist Alexander Mikhailovich Butlerov. I think that's how you say it. And I drew a diagram here. Here's where we're going to go, at least if you have any other extra ideas. You have your Jupiter, or similar star. You have your asteroid. It has a very small surface area. It slams into it. And what happens is three specific things happen once it slams into it. You'll have it breaks up to increase the surface area for increased rates of reaction and larger, more complete reactions. Think about when you burn steel wool with a lighter. The reason why you can burn steel is because the surface area is a lot greater, being that it's steel wool. and that oxygen can get to it and it can burn. But if you took like a plate of iron or iron brick or a steel brick and you tried to burn it with a lighter, nothing would happen. As well, it heats up the material to allow for specific chemical reactions to take place and increase the rates of chemical reactions. Naturally, in chemistry, when you heat stuff up, if there's any kind of chemicals in there that react better with heat, when you introduce heat to it, it'll take place faster, or it'll be more complete reaction, you know, you name it. So basically, you have a really cold, higher atmosphere on an intermediate age star such as Jupiter, where it sits around 200 Kelvin, and you have a large asteroid slamming into it. It'll break up into a bunch of bits, allow for the catalyst iron to combine all that formaldehyde that's in the vicinity to make simple sugars. And if you have a 200 Kelvin atmosphere, that's not a problem. When you have an asteroid slamming into it that's the size of a small city, I guarantee you it's going to be really goddamn hot. It's going to be well over 5,000 Kelvin in some areas, and that's going to make it to where it can both mechanically mix it, heat it up, and break apart the catalyst to make sure that those reactions can take place. So you look at it as a giant chemistry experiment, if you will. But yeah, that's where I'm headed. Take whatever you want out of this talk. There's a lot more work to do, but now I'm really starting to branch off and to name specific chemical reactions to take place once I laid the foundation for the fact that, you know, chemistry happens inside of evolving stars. And that's just completely lost among the astronomers. You know, they're still in their little la-la land with black holes and big bangs and stuff. But hopefully that helps. Later, man.